So earlier I'd shown you what a Turing machine is. I gave you some background on what Turing machines are. And we talked about a couple basic examples of Turing machines and how they work. So namely, we talked about this idea of halting. We talked about this idea of accepting or rejecting input. But it's worth noting that sometimes, as we actually seen with one of our examples, this idea of accepting and rejecting doesn't actually make a whole lot of sense to do. You want to think more about Turing machines as this more functional machine, as opposed to a decision-based machine where it says yes or no. I just want it to perform a task. I want to do some sort of function. I want to apply, I want to take the input, I want to do something with it. Many formal concepts in theory computation come from the idea I'm going to show you here. Namely, you may have heard of things such as, you may have heard of something called a reduction, for example. They're actually built on this idea that I'm going to show you in a moment here. So we're going to talk about what our special kind of Turing machine is called a transducer. So we're going to talk about transducers. So just as a reminder, like most computers output from input. So maybe I would like to have that for my Turing machine. So our machine's output could be left on the tape. On the tape when the machine halts. So once the machine processes, I want it to stop, and whatever's on the tape, I want to be able to interpret that as output. Okay? So that's the main idea here. So very often when we think about a transducer, I imagine I'm given some input. Oftentimes that input may be given as some sort of collection of values. So often we like to think of it as I give you like the first value of the input, some separator or comma, whatever kind of symbol. I need some symbol to separate them, which often are called separators. I'll have the first value, separator, second value, separator, third value, separator, and so on. This is very much in the same vein as like I gave you a function, it has inputs, I need to encode that onto the tape so I can use it. So that's the idea I want you to keep in the back of your mind. So as I've said before, Turing machines, well, we have thought of Turing machines as recognizers. So that means give me some input. It tells me yes, accept, or reject. But mainly we're interested primarily in acceptance. So if I give you an input string, it's got to tell me yes, that is a string of the formal language I'm interested in. Or if I'm answering some question to a problem, I want to know when the answer is yes. So Turing, so we'll talk about Alan Turing. Turing actually considered, that consider is very interesting, considered originally a computer of integer valued functions in a manner like we will see. So in Turing's scheme, each integer, so we're given these integers, which are encoded. They may be encoded in unary or binary. and so on. And the idea is that I take in input, leave output on the tape. So we will consider special kinds of Turing machines called transducers. And since we're not interested in a final state or accepting or rejecting, and when defined, the set of accepting or final states is typically omitted because we're not interested in accepting or rejecting. We just want to do some processing. But that processing needs to finish at some point for the transducer. So you know how I gave you a 7 tuple? You're going to think of this as a 6 tuple. So you're just going to chop off the last object, which is the set of final states. So if you start seeing 6 instead of 7, that's why. We don't care about accepting and rejecting. But let's talk about it now. Let's do an example. So I promised you we would see how we could do some things with these Turing machines. We already seen how it can convert symbols into other symbols. In a very basic example, we also seen how to process strings that belong to some regular expression. Let's talk about addition. So we're going to do what we call unary addition. So we're going to consider unary addition. Now, how many of you have never heard of unary before? It's okay if you've never heard of unary before. And you may have heard of decimal. You may have heard of binary. You may have heard of all sorts of different number systems. Unary is actually really simple. So, you know, binary uses symbols 0 and 1. Decimal uses 0, 1, 2, 3, 4, 5, all the way up to 9. So this is 10 symbols. Unary, the big tip with unary is this part here. It's sort of hiding there, but it means one. It means 1. So this is base 1, okay? So this is a very special numeric base, by the way. It has very strange properties in theory of computation, but it's worth noting that this is what we're going to look at. So, for example, I could give you a number in unary by just using one symbol. For example, I could give you like 0, 0. Those are, so this, for example, there's 2 zeros there. Well, let's put 3 here. This is using one symbol, namely the symbol 0. Some people use ticks, for example. You may actually be quite used to unary before. Don't let the fact there's zeros throw you off. What do you do when you tally? You know, you're sitting there and you're counting things. Like you're watching poor me playing some game and I keep failing over and over again or something. You keep a tally, right? See, like you would have like a tally that keeps count of things, right? So you can have ticks. Well, what you're actually doing is you're counting in unary. Except don't count the whole slashing with a cross. That's a whole other rule. But say, for example, if I have 1, 2, 3, 4, 5, 6, this is 6 in unary. So 6, so that's 6. If I use zeros as the single symbol, this would be 3. But what we'll do for our little exploration here is we're going to use zeros rather than ticks. And instead, I'll use the separator. As a separator, I'll use a 1. Just because it looks kind of like a separator. It kind of separates the zeros. So, for example, if I give you something that looks like this, like 0, 0, 1, 0, 0, 0, what I'm saying is, okay, this number, that's 2. This number, that's 3. Because it's the number of zeros. Is that clear, everybody? So, this is just another way of representing a number. We're only using one symbol to represent it, though. So So notice I have 2 zeros, so that's the number 2. I have 3 zeros, so that's the number 3. So when I write out and I want to add numbers, like I said just a moment ago, I want to give you the values as input, and I want to do some processing. So what it's going to look like when we consider adding two numbers in Unary is I'm going to give you some number in Unary, and then I'm going to have a separator, and then I'm going to have some other number in Unary. I have a question for you. Question. What's 0 in Unary? What's 0 in Unary? It's like the number 0. So most certainly, like, if I give you like this, that's 1, right? It's not 0, right? Because that's just the symbol. It's no different than if I wrote only one tick down. But what's 0 then? It's not the symbol 0, right? What we care about is the number of the symbols, right? So if it's 0, how many zeros are there written down, say in this kind of form like this? What would it look like? So say, for example, I want to go 0 plus 1. So, for example, what I'm going to be doing in this example is I would like to add these two numbers, and I want to get the result. So, for example, I would want to get it so it could be 5, where the answer should look like this, right? So if I give you 0 in Unary, it might look something like this. So notice there's no zeros over here, but I have like 1 0 here, so it makes that 1. So this would be like 0 plus 1, which equals 1. So the answer here should just be a single 0. So what I want to show you is how we could come up with a Turing machine that adds numbers in Unary. And believe it or not, it's going to feel like we're cheating. Because Unary is very simple. But I already get the idea of how Unary works. So it's no different, other than the cross rule that you use when you're tallying, when you count up 5s or 10s. It's no different than tallying. So how many ticks there are, or how many zeros I write, whatever symbol I decide to use. If I want to use happy cat faces as the symbol, I can use happy cat faces. It doesn't matter. The whole point is that it's the number of the symbols. That tells me the magnitude, or what the value is. So don't let the fact there's zeros throw you off. They're just the number of symbols that matters. So what we're going to do in our example here is we're going to come up with a Turing machine. What we're going to do is we're going to perform addition where numbers are in Unary separated. Let's go separated by a marker. So first, we're going to have these numbers. The numbers are going to have the form as follows. So I'm going to use zeros to represent the quantities. I'm going to use a 1, like I said, as a separator. So I know what the two values are. Assume input. So this is an assumption I'm making. So assume the input is given in the form. So it should look like this on the tape. It should be 0 to the m, 1, 0 to the n, where m and n are greater or equal to 0. So if you're not familiar with this notation, the exponent says repeat what is written there that many times. So for example, if m is 2, this says write 2 zeros. If this is 3, this says write 3 zeros. So keep in mind that if it's the exponent 0, then it's just the empty string, because I wrote no zeros. So let's think about this. So what should the output look like then on the tape when we're done? What does Unary addition actually do? Think about it. Okay. it's, like I said, it's going to feel like we're cheating, but it's not. This is how it works. And there's many different Turing machines you can describe to do this. So for example, I have two examples here. I have like 2 plus 3 gives me 5. I have 0 plus 1 gives me 1. So what can I say that looks like what actually is happening if I want to get the answer? Well, remember, the number of times I write down the symbol is the magnitude of it's the value, right? So think about it. Okay. Now I'm going to do something, and you're going to see it. Just watch. I want you to carefully look at this example. Remember, this is just an example. So I have 5 over there. It's 5 zeros. Watch this. Look at that. There's 5 zeros. So if there's any way I can get rid of that separator, I can get the answer. So if I could design a Turing machine that takes and removes the separator and then shuffles the zeros over in some way, then I'm done. So that's what I need to come up with as a transducer. So remember, a transducer is just a special kind of Turing machine. We call it a transducer because it doesn't accept or reject. So let's figure out what we're going to do with this. So remember, now that we know that, what should the answer be? So the output that should be left on the tape then should be 0 to the m plus n. Boom. So now we have to come up with the machine now. Let's do that. So remember, we want to come up with this one main idea, is we want to get it so we can get rid of that separator. But here's the thing. There's a lot of ways we could do this, and if we do it the wrong way, we're going to get the wrong answer. So we have to be careful. So first, here's an idea. Well, let's kind of bat around a couple ideas of how we could do this, okay? So I have like 0, 0, 0, 0, 0, like this. Now, let's kind of see a couple ways we could go about this and see if they make sense or not. So first, I can have zeros. So remember, this is just an example. The Turing machine needs to work with an arbitrary string that looks like that. So let's see here. So what I could do, here's an idea. I'm just going to throw a couple ideas out. One of them ultimately has to make the most sense. So maybe what I should do is see if I can find a 0. Maybe I like go over here and then I move back here and put a 0 here. Maybe I can like do this. That's an idea. That's maybe one idea maybe we can try. Anybody see any problems with that approach? Anything interesting about that approach? So reminder, what I did was I looked for a 0 on the rightmost side. I turned it into a blank, then I moved left, and then I put a 0 where there was a 1. Is there any ideas of what's going on here and if that makes any sense to do? So is there any assumptions I'm making when I do something like that? Well, let's think about it. Let's walk through the process again. What I did was I took a 0, so I went right. Remember, the Turing machine will start here. I would make it go right. I go here, put a blank there. Then I would switch to another state that goes and searches left for a 1, and I replace it with a 0, and then I would stop. What's the underlying assumption here if I do something like that? Well, what's actually kind of neat is that this won't work in general because remember we have the situation such as this where it's like 0 plus 1 where I can have no zeros. Well, what if it's 1 plus 0 and I go seeking out a 0 after the separator? Well, let's look at it. Let's see what this would look like. So this would be like if it was 0, 1 like this. Well, I would go look past the separator and I'll go find a 0, but I won't find a 0. Well, that's a problem, right? I can't do that. So this idea would fail. So I can't use that approach. So I have to consider the fact that it could be that there's no zeros on the left-hand side of the 1 or on the right-hand side of the 1. So we have to be a bit more careful about how we think about this. It's not as simple as just I need to do something to move to put a 0 somewhere, but I need to make sure I do it carefully. So it's not necessarily that I need to I have to be a bit careful, right? So let's think about this. So maybe I should think about this a little differently. So we know that approach doesn't work because of this edge case. Because the underlying assumption is, and keep in mind that's just as true if I were to take it from the left bank of zeros. It's because I've assumed here that it's actually that I can have no zeros. That approach might make more sense if I had at least 1 0. If I always had at least 1 0, that maybe an approach like that might work, depending on what the assumptions are with those zeros. Okay, let's think about it. Let's think about let's go back to this example again. Remember, these are just to help us think about it. This is not showing us that it works arbitrarily. Okay, so let's think about this a little differently. Because remember, we know as a matter of fact, there could be the case that there's no zeros right here. There could also be no zeros right here. However, I always know there's a 1. I always know there's a 1. So on the input, if there's no zeros, it'll just be a 1 first. So I have an idea. Why don't we focus on the 1 here and then try to find the last 0 and then make that a blank. So let's see what that would look like here. So I would search for a 1. I find the 1. I change it to a 0. So I go that way. I change it to a 0. Then I look for the last 0 by going right. And then I turn it into a blank. Interesting, right? So notice that this seems to work for this particular example, right? Well, how about let's look at for example the one we had over here that didn't work. Okay, I'm going to locate the 1. I change the 1 to a 0. And then I'm going to now look for the last occurring 0. Notice that I'm at the last occurring 0, so I'm going to turn that into a blank. Interesting, right? So now this seems to make sense, right? Do you see how instead of we're assuming there is a 0 and I'm going to go erase it, I'm going to go and put and assert that that 0 is to exist. And if I can't find it, I get rid of the new 0 I added. So it's kind of like +1, -1, that kind of thing. So this idea, however, seems to make a lot more sense. So why don't we design a Turing machine that does this? So I'm going to describe this using a transition table. And I'm going to give a description of what's happening for each of them. So I'm going to give each state a job. And you'll find with Turing machines, this makes a lot more sense to do than, say, with previously when you think about like DFAs. Here it actually makes a lot more sense to talk about them like as them having jobs or a task that they're doing. So we're going to have a state. We're going to have, remember the different tape symbols. We'll have a 0, 1, or a blank. And then we're going to have a description. We'll have a description. So we're going to have, now remember, let's walk through this process again. What did I do? The first thing I did was what? Remember, if I have like, what I do? I find the marker or separator, right? That's the first job I have. So that's maybe the first state's job. So for Q0, what I'm going to do is I'm going to find find the marker, and we're going to make it 0. That's what Q0's job is. That's its sole job. So think of this like we're trying to think of it almost like we're taking the problem and decomposing it into pieces, which a lot of people, especially if they've done any programming, this is a pretty common way of thinking of problem solving. And this is, you're going to find that this is actually rather helpful here, is you break the task into smaller pieces, you assign those maybe to different states. You may need 2 or 3 states to do it. It's hard to say, depends on what you're looking at. So let's think about this. So if I see a 0, what did I do? I go past it, right? I want to find the 1. So we're going to stay in Q0. Remember the 3 things we need to know. The state we're going to change to, what tape symbol you're going to write, and what direction you're going. So I want to keep going right until I find the 1, right? When I find the 1, I want to go to my next job, my next task. So I'm going to replace the 1 with the 0, just like what I'm going to do. And I'm going to go write 1. And if we see a blank, definitely don't do anything. Don't do anything. Remember, we're working on the assumption that the first symbol we're going to see is either a 0 or a 1, not a blank. So that's the first state. Next, we need another job here. We're going to try to find the last 0. We need to search for it. Now, this is where it gets a little bit funky. We have to be careful. Because how do we do that? We have to be very careful about this, right? Because remember, we can always have the funny edge case. Like here it's fine. Like I can like, okay, I change that to a 0. And then I go searching. I scan all the way. Now, do I want to stop here? Well, on a Turing machine, you don't know if you hit the end until you see the blank, right? So we're going to need to keep going until we see a blank symbol on the tape. So we're going to have to like find the blank symbol first, then we go left, and then we can delete. And since I've introduced a 0, this will always take away a 0 if I were to think of it like that. So what we're going to do is we're going to go as far right as we can over the zeros until we find a blank. Does that make sense to everybody? I'm hoping that makes sense. Because we need to know when we hit past the input. We need to go past the input to actually do this. We can't just stop here. We don't know if there's another 0 after it. So with Q1, we're not going to change any of these zeros, keep them the same. We know there's no more 1s, so we're just going to keep going. But we want to go into the next state once we see the blank. So we'll leave the blank alone, and when we get that, we hit the blank, it's going to move the tape head 1 to the left. And if we do that, that will land us where we inserted a 0. But we're not quite done yet, right? We have to actually erase the last 0. Let's erase the last 0. So when we actually find it, so for the sake of ease, what we would do is we would turn that into a blank. But let me show you what it looks like for that funny edge case. So say, for example, it's just a 1. Where there's no zeros anywhere. The answer here should be 0, right? So it should just be blanks everywhere on the tape. So we know it starts here. This gets changed to a 0. It moves the tape head to the right, finds the blank, and says, okay, well, now go to Q2, but on that you're going to go back left. It'll land you right here, back on the 0. Now we need to turn that into a blank. And we know that 0 always exists because we took a 1 and turned it into a 0. Somewhere. There has to be at least one of them. That's that one of these zeros that's sitting there on the tape, which we just had to have found, most certainly is the one that we need to turn into a blank. So we're going to erase the last 0. And then finally, we're going to move into the final state. But remember, transducers don't have final states, right? We just wanted the halt. And there's your Turing machine that takes and adds 2 unary numbers. So if you were to take and draw out some tape, your tape, and do what we did in some of our earlier examples with this transition table, you'll be able to take any 2 unary numbers. If you write the value in terms of the number of zeros, you'll be able to add 2 numbers. Neat, right? So I'll leave it up to you if you want to draw this as a transition diagram. And remember, it has no final states, so you're not double circling any states if you're drawing one of those. It just has a start state if you're thinking about like special states. Okay, so that's a pretty neat example, right?